Tonight, we're going to talk about something that will completely shatter your sense of scale in the universe. We're going to explore the biggest galaxy ever discovered. Not just big, not just larger than the Milky Way, but so unfathomably enormous that when astronomers first realized what they were looking at, they had to double-check their measurements because it seemed impossible. This galaxy is so large that light takes over 16 million years just to cross from one end to the other. By the end of tonight, you're going to understand what this galaxy is, how it got so massive, and what it tells us about the invisible forces shaping our universe. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let me start with something you need to understand about galaxies in general. When most people think of a galaxy, they picture a beautiful spiral like the Milky Way or Andromeda. Bright core, sweeping arms, filled with stars, maybe some dust lanes cutting through the structure. These images are what we see in telescope photographs, what gets printed on posters and shown in documentaries. They're stunning and they're real, but they're incomplete. Because what you see in those images, the visible light from stars and glowing gas, is only part of what's actually there. Galaxies are more than just the stars you can see. They're surrounded by vast halos of dark matter, invisible material that doesn't emit or absorb light, but exerts gravitational pull. They're embedded in clouds of hot gas that glows in X-rays, but is invisible to optical telescopes. And in some cases, they have enormous structures extending far beyond the visible galaxy. Structures made of plasma and magnetic fields that stretch across intergalactic space. These extended structures are created by supermassive black holes at the centers of galaxies. The black holes don't just sit there passively. They actively feed on surrounding material, and as matter falls toward them, it doesn't all get swallowed. Some of it gets accelerated to nearly the speed of light and shot outward in gigantic jets. These jets carry energy and particles away from the black hole, out past the visible edges of the galaxy, far into the void between galaxies. And in radio wavelengths our eyes can't see, but our telescopes can detect. These jets appear as enormous glowing lobes extending from the galaxy like wings. These are called radio galaxies, and the galaxy we're talking about tonight is the largest radio galaxy ever found. Its name is Alcyonius, named after a giant from ancient mythology, and the name fits because this galaxy is absolutely colossal, from end to end. Measuring from the tip of one radio lobe to the tip of the other, Alcyonius spans approximately 16.3 million light-years. Let me put that in perspective. The Milky Way, our home galaxy, is about 100,000 light-years across. Alcyonius is 163 times wider. If you place the Milky Way at one end of Alcyonius, you'd need to line up 163 Milky Ways side by side to reach the other end. Andromeda, the largest galaxy in our local group, is roughly 220,000 light-years across. Alcyonius is still 74 times wider than that. Even IC 1041, which used to hold the record for the largest galaxy, measures around 6 million light-years across. Alcyonius is nearly 3 times larger. To cross Alcyonius at the speed of light would take over 16 million years. Light that left one end of this galaxy 16 million years ago is only just now reaching the other side. 16 million years ago, Earth was in the middle of the Miocene epoch. Our ancestors were small apes, living in forests. No humans existed yet. And here's what makes this even more remarkable. Alcyoneus wasn't discovered until 2022. The data that revealed it had been sitting in astronomical archives for years. Astronomers had looked at this region of sky before, had collected the radio observations, but nobody had pieced together what they were seeing. The galaxy was hiding in plain sight. It took a team of astronomers, led by Martijn Oey from Leiden Observatory in the Netherlands, to finally recognize what was there. They were analyzing data from the LOFAR telescope, the low-frequency array, a radio telescope network spread across Europe. LOFAR observes the sky at very low radio frequencies. Frequencies that can detect the faint glow of extended radio structures that higher frequency telescopes might miss. The team was specifically looking for giant radio galaxies, trying to find the largest structures in the universe. And when they processed the LOFAR data with new techniques designed to enhance faint, extended emission, Alcyoneus emerged from the noise. At first, they weren't even sure it was all one object. The radio lobes extended so far that it seemed unlikely they could all be connected to a single galaxy. But as they analyzed the structure, they confirmed it. One host galaxy, one supermassive black hole, two jets extending in opposite directions, and two massive radio lobes at the ends of those jets, all part of one system. Alcyoneus sits approximately 3 billion light-years away from Earth, in the direction of the constellation Lynx. 3 billion light-years means we're seeing Alcyoneus as it was 3 billion years ago, when the universe was about 78% of its current age. Earth was still young. Single-celled organisms dominated life, and multicellular life was only beginning to emerge in the oceans. The light that left Alcyoneus back then has been traveling through space ever since, crossing the vast emptiness between galaxies, and it's only now arriving at our telescopes. So, what we're seeing is ancient history, a snapshot of this galaxy from billions of years in the past. Now, let me explain what Alcyoneus actually looks like, because it's not what most people would expect. The host galaxy itself, the central galaxy where all the stars and the supermassive black hole reside, is actually fairly ordinary. It's an elliptical galaxy, meaning it doesn't have spiral arms. Elliptical galaxies are more blob-shaped, collections of stars moving in random orbits rather than the organized rotation you see in spirals. This host galaxy contains somewhere around 240 billion times the mass of our Sun. That's a lot, but it's not exceptional. The Milky Way has a similar mass. There are many galaxies far more massive than Alcyoneus's host. The supermassive black hole at the center has a mass estimated at around 400 million times the mass of the Sun. Again, that's large, but not uniquely so. Some supermassive black holes are billions of solar masses. The black hole at the center of the Milky Way, Sagittarius A, has a mass of about 4 million solar masses, so Alcyoneus's black hole is about 100 times more massive, but it's not the largest black hole we've found by any means. So the central galaxy and its black hole are relatively normal. What makes Alcyoneus extraordinary are the jets and lobes extending from that galaxy. These structures are visible only at radio wavelengths. If you looked at Alcyoneus with an optical telescope, you'd see a faint elliptical galaxy and nothing else. The lobes are completely invisible to the human eye. But when radio telescopes observe this galaxy, they reveal enormous plumes of energized plasma extending millions of light-years into space. These lobes glow with synchrotron radiation, light emitted when electrons spiral around magnetic field lines at nearly the speed of light. The electrons were accelerated by the black hole's jets and are now spreading out into intergalactic space, creating these vast, glowing regions. The jets themselves are relatively narrow, like cosmic fire hoses, shooting plasma outward from the black hole at velocities approaching the speed of light. But once the jets reach the end of their journey, they spread out, forming the lobes. Think of it like a garden hose spraying water into a pool. The stream is narrow and fast, but when it hits the water, it disperses, creating a broader area of turbulence. The jets from Alcyonius have been active for an extremely long time. To inflate lobes this large requires tens of millions, possibly hundreds of millions of years of continuous energy output. The black hole has been feeding and launching jets for longer than humans have existed, longer than most species on Earth have existed. And the energy involved is staggering. The total energy contained in these lobes, the energy required to accelerate all that plasma to such high speeds and spread it across 16 million light-years, is roughly 10 to the 61 joules. That's a 1, followed by 61 zeros. For comparison, the Sun outputs about 3.8 times 10 to the 26 joules per second. To produce the energy in Alcyonius's lobes, the Sun would need to shine for roughly 10 to the 34 seconds. That's about 300 trillion years, far longer than the current age of the universe. So, even though the host galaxy seems ordinary, the black hole has accomplished something extraordinary. It has created the largest known galaxy-scale structure in the universe. But this raises an obvious question. Why is Alcyonius so large? What allowed it to grow to this size when most radio galaxies, even those with similarly massive black holes, are much smaller? This is one of the central mysteries about Alcyonius, and astronomers don't have a complete answer yet. But they have some ideas. One possibility is time. Maybe Alcyonius's jets have simply been active longer than most other radio galaxies. If the black hole has been feeding continuously for hundreds of millions of years without interruption, the jets would have more time to push outward, inflating the lobes to enormous sizes. Most radio galaxies might go through active phases where the black hole feeds and launches jets, followed by quiet phases where the jets shut off. Alcyonius might have avoided those quiet phases, staying active long enough for its lobes to grow exceptionally large. Another possibility is the environment. The space between galaxies isn't completely empty. There's intergalactic medium, a very thin gas that fills the voids. This gas is extremely sparse, far more tenuous than the best vacuum we can create in laboratories on Earth. But it's there, and it can resist the expansion of radio lobes. If Alcyonius happens to be in a region of space where the intergalactic medium is particularly thin, where there's less gas to push against, the jets could expand farther before being stopped. Think of it like blowing up a balloon underwater versus blowing up a balloon in air. In water, the resistance is higher, so the balloon doesn't expand as easily. In air, there's less resistance, and the balloon can grow larger. If Alcyonius is in a relatively empty region of intergalactic space, a cosmic void with less gas than average, its lobes could expand more easily. Observations do suggest that Alcyonius is located in a relatively underdense region, supporting this idea. A third possibility is the power of the jets themselves. Maybe Alcyonius's jets, despite coming from a relatively normal black hole, are somehow more powerful or more persistent than typical jets. Small differences in how the black hole feeds, in the geometry of the accretion disk around it, or in the magnetic fields threading through that disk could result in jets that carry more energy farther from the galaxy. There's also the question of orientation. The jets from Alcyonius are oriented roughly perpendicular to our line of sight, meaning we're seeing them from the side rather than looking down the barrel of one of the jets. This is actually ideal for measuring the full extent of the structure. If the jets were pointed more toward us or away from us, projection effects would make them appear smaller. So part of why Alcyonius appears so large might be a matter of lucky geometry. We're viewing it from the perfect angle to see its true size. But luck alone doesn't explain why the structure exists in the first place. Even accounting for orientation, Alcyonius is genuinely enormous. There's something about this system, whether it's age, environment, jet power, or some combination of factors that allowed it to grow beyond what we typically see. And studying Alcyonius helps astronomers understand the extremes of what's possible, the upper limits on how large these structures can become. Before we dive deeper into what's in those lobes, let me explain how radio astronomy actually works, because understanding this will help you appreciate just how remarkable the discovery of Alcyonius really was. When most people think of astronomy, they think of optical telescopes looking at visible light, the kind of light our eyes can see. And that makes sense, because that's how we experience the universe directly. We look up and see stars as points of light. But visible light is just one small part of the electromagnetic spectrum. Light comes in many forms, many wavelengths, and our eyes can only detect a tiny fraction of it. The electromagnetic spectrum runs from radio waves at the long wavelength end through microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays at the short wavelength end. Each of these wavelengths reveals different aspects of the universe. Hot, young stars emit lots of ultraviolet light. Warm dust glows in infrared. Extremely hot gas emits X-rays. And the energized plasma in structures like Alcyonius's lobes emits radio waves. Radio waves have wavelengths ranging from millimeters to meters to even kilometers. They're much longer than visible light waves, which have wavelengths measured in nanometers, billionths of a meter. This means radio telescopes need to be built differently than optical telescopes. An optical telescope uses mirrors or lenses to focus light to a point. A radio telescope uses a large dish, an antenna that collects radio waves and focuses them to a receiver. The larger the dish, the more radio waves it can collect, and the better resolution it can achieve. But there's a problem. To get high resolution at radio wavelengths, you need enormous dishes, much larger than any single telescope we can build. So, astronomers developed a technique called interferometry. Instead of one giant dish, you use multiple smaller dishes spread across a large area. You collect radio signals at each dish simultaneously. Then you combine those signals using computers. The result is a resolution equivalent to a telescope as large as the distance between your dishes. This is how LOFAR works, the telescope that discovered Alcyonius. LOFAR isn't one telescope. It's a network of thousands of small antenna stations spread across Europe. Most are in the Netherlands, but there are stations in Germany, France, the UK, Poland, and other countries. When you combine the signals from all these stations, you create a virtual telescope hundreds of miles across. And that gives you the resolution and sensitivity needed to detect faint, extended structures like Alcyonius's lobes. LOFAR operates at very low frequencies, between 30 and 80 MHz and between 120 and 240 MHz. These are among the lowest radio frequencies used for astronomy. Lower frequencies have longer wavelengths, which makes them perfect for detecting large diffuse structures. Higher frequency radio telescopes might miss these structures entirely because they're optimized for detecting compact sources. LOFAR's low frequencies also penetrate through ionized gas more easily, revealing structures that might be hidden at higher frequencies. This is crucial for finding giant radio galaxies like Alcyonius. The discovery itself involved processing massive amounts of data. LOFAR constantly scans the sky, collecting data on millions of radio sources. The raw data from a single observation can be terabytes in size. Processing this data requires specialized software that can handle the complexity of combining signals from thousands of antennas. The team that discovered Alcyonius developed new techniques to enhance faint extended emission. Most radio sources in the sky are compact, bright spots like quasars or the cores of active galaxies. The software used to process radio data is usually optimized for finding these compact sources. But giant radio lobes are different. They're faint, they're spread out over huge areas of sky, and they're easy to miss if you're not specifically looking for them. The team modified their data processing to subtract out the bright, compact sources and enhance the faint, diffuse emission. This is like adjusting the contrast and brightness on a photograph to bring out details that were hidden. And when they did this, Alcyonius appeared. The lobes emerged from the background noise, revealing their full extent for the first time. It's a testament to how much we can miss, even when we're looking directly at something. The data showing Alcyonius had been in the archives for years. Other astronomers had observed this region of sky, but nobody had processed the data in quite the right way to see what was there. This happens more often than you might think in astronomy. We collect far more data than we can fully analyze. Telescopes take observations. The data gets archived, and sometimes it sits there for years before someone takes a fresh look at it with new techniques or new questions in mind. And sometimes, like with Alcyonius, that fresh look reveals something extraordinary. Now, let's talk about what's actually in those lobes, because they're not just empty space glowing with radiation. The lobes contain plasma, ionized gas, where electrons have been stripped from atoms. This plasma is incredibly hot, with temperatures reaching millions of degrees Fahrenheit or millions of degrees Celsius. But it's also incredibly diffuse. The density is so low that in a volume the size of a sugar cube, you'd find only a handful of particles. That's far more empty than the best vacuum chambers on Earth. The plasma is threaded with magnetic fields. These fields are what keep the plasma somewhat organized, preventing it from dispersing completely. The electrons spiral around the magnetic field lines, and this motion produces the synchrotron radiation that makes the lobes visible at radio wavelengths. The lobes are also in motion. They're expanding outward, pushed by the jets. As they expand, they sweep up the sparse intergalactic medium, creating a bow, shock at their leading edges. This is similar to the shock wave a supersonic jet creates in Earth's atmosphere, except it's happening on a galactic scale in an incredibly thin gas. Over time, the lobes will eventually fade. If the jets shut off, if the black hole stops feeding and stops launching new plasma into space, the lobes will gradually lose energy. The electrons will slow down, the synchrotron radiation will weaken, and eventually the lobes will become too faint to detect. This process takes millions of years, so we can still see lobes from jets that shut off long ago. Some radio galaxies have visible lobes, but no currently active jets, remnants of a previous active phase. Alcyonius's jets appear to still be active, still feeding the lobes, which is part of why they've grown so large. But someday, millions or billions of years from now, those jets will stop, and the lobes will begin their slow fade into invisibility. One of the fascinating things about Alcyonius is what it tells us about supermassive black holes and their relationship with galaxies. Every large galaxy has a supermassive black hole at its center. This isn't speculation, it's observational fact. We've detected these black holes in galaxy after galaxy using multiple methods. We see stars orbiting invisible massive objects at galactic centers. We see gas swirling in accretion disks. We see jets launching from galactic nuclei. All of this points to the presence of black holes, with masses ranging from millions to billions of times the mass of the Sun. Let me explain how these black holes actually create jets, because the physics involved is fascinating and not widely understood. A black hole itself, by definition, is a region of space-time where gravity is so strong that nothing, not even light, can escape. So how does a black hole, an object that traps everything, manage to launch jets of material traveling at nearly the speed of light? The answer is that the jets don't come from inside the black hole. They come from the material surrounding it, from the accretion disk. When gas falls toward a black hole, it doesn't fall straight in. It has angular momentum, rotation, which causes it to spiral inward. As it spirals, it forms a disk, much like water spiraling down a drain. This disk is called an accretion disk, and it's where the real action happens. The gas in the accretion disk is moving at extremely high speeds, orbiting the black hole at significant fractions of the speed of light. Friction between different parts of the disk heats the gas to millions of degrees. This hot gas emits enormous amounts of radiation, visible light, ultraviolet, X-rays, all across the electromagnetic spectrum. In fact, an actively feeding black hole with a bright accretion disk can outshine the entire galaxy it's in. All that light is coming not from the black hole itself, but from the superheated gas in the disk around it. Now, here's where it gets interesting. The accretion disk is threaded with magnetic fields. These fields are carried inward with the gas as it spirals toward the black hole. Close to the black hole, where the gravitational forces are strongest and the disk is rotating fastest, these magnetic fields get twisted and amplified. The spinning accretion disk acts like a dynamo, strengthening the magnetic fields and organizing them into a particular configuration. Some of these field lines thread through the disk, but others loop up above and below it, forming a magnetic funnel. Material flowing along these field lines gets accelerated to enormous speeds. It gets focused into narrow beams, shooting out perpendicular to the disk, away from the black hole. These are the jets. The material in the jets is moving at velocities approaching the speed of light, 90%, 95%, sometimes even 99% of light speed. At these speeds, relativistic effects become important. Time dilates, lengths contract, and the material carries enormous amounts of energy. The jets punch through the gas surrounding the galaxy and keep going, out into intergalactic space. As they travel, they push against the thin intergalactic medium, creating bow shocks and inflating the lobes we see at radio wavelengths. The electrons in the jets spiral around magnetic field lines as they travel, and this motion produces synchrotron radiation, the radio waves we detect. Different radio galaxies have jets with different properties. Some jets are straight and narrow, like cosmic fire hoses. Others are bent and twisted by interactions with surrounding gas or by the motion of the galaxy through space. Some jets are one-sided, meaning we can only see one jet, while the other is pointed away from us and too faint to detect. Others are two-sided, like Alcyonius, where we see both jets clearly. The power carried by these jets is staggering. For Alcyonius, the jets are transporting something like 10 to the 44 joules per second away from the black hole. That's 10,000 trillion joules every second. For comparison, the total power output of the Sun, all the light and heat it produces, is about 4 times 10 to the 26 joules per second. Alcyonius's jets are carrying away about 100 million trillion times more power than the entire Sun produces. And this has been going on for tens of millions of years, possibly hundreds of millions of years. The total energy pumped into the lobes over that time is almost incomprehensible. It's enough energy to accelerate billions of suns to significant fractions of the speed of light. And it all comes from matter falling into a black hole 400 million times the mass of the Sun. The efficiency of this process is remarkable. When matter falls into a black hole, some of its mass energy can be converted to other forms of energy and ejected in jets. For a rotating black hole, up to about 42% of the infalling mass can be extracted as energy in this way. That's far more efficient than nuclear fusion, which converts less than 1% of mass to energy. A black hole jet is one of the most efficient energy extraction mechanisms in the universe. There's another peculiar property of jets that's worth understanding. The material in jets travels at nearly the speed of light, but the jets themselves can appear to move even faster than light when viewed from certain angles. This is called superluminal motion, and it's a relativistic effect. It doesn't violate the speed of light limit. It's an illusion created by the geometry and the time it takes light to reach us. Imagine a jet pointed almost directly toward you, but not quite, maybe at a slight angle. Material in the jet is moving toward you at 99% of light speed. It emits light as it travels, and that light also travels toward you at light speed. But because the material is moving almost as fast as the light it emits, the light emitted at different times doesn't have to travel very different distances to reach you. It all arrives in a compressed time window. When you measure how far the material appeared to move and divide by the time between observations, it can look like the material moved faster than light. But it didn't. It's just a projection effect combined with the finite speed of light. This was actually confusing when it was first observed in the 1970s. Astronomers saw features in jets apparently moving at several times the speed of light and didn't immediately understand what they were seeing. It took careful analysis and modeling to realize it was a relativistic effect, not actual faster-than-light travel. Alcyonius's jets are oriented roughly perpendicular to our line of sight, so we don't see this superluminal motion. We're viewing the jets from the side, which gives us a clear view of their full length, but doesn't produce the foreshortening effects that create apparent superluminal speeds. And there's a strange relationship between the mass of a galaxy's central black hole and the mass of the galaxy's central bulge, the dense concentration of stars at the galaxy's core. More massive bulges have more massive black holes, and the relationship is remarkably tight. A galaxy's central black hole typically has a mass of about 0.1 to 0.5% of the bulge mass. This sounds like a small fraction, and it is. But it's a very consistent fraction across a wide range of galaxy masses. Small galaxies with small bulges have proportionally small black holes. Giant galaxies with massive bulges have proportionally massive black holes. The relationship holds across more than 4 orders of magnitude in mass. This suggests that black holes and galaxies grow together, that they co-evolve over cosmic time. When galaxies merge, their black holes eventually merge too, creating larger black holes. When gas flows into a galaxy and forms new stars, some of that gas also feeds the central black hole, allowing it to grow. And when the black hole feeds, it can launch jets like those we see in Alcyonius. These jets pump enormous amounts of energy into the surrounding environment. They heat the gas in and around the galaxy, preventing it from cooling and collapsing to form new stars. This is called feedback, and it's a crucial process in galaxy evolution. Without black hole feedback, galaxies would form stars too efficiently, turning all their gas into stars in a relatively short time. But the energy from jets and from radiation emitted by material falling into the black hole disrupts this process. It heats the gas, blows it away, and regulates how fast stars can form. Computer simulations of galaxy formation show that if you don't include black hole feedback, you get galaxies that are far too massive and too blue, meaning they have too many young stars. Real galaxies are more moderate in their star formation, and that's because black holes regulate the process. Alcyonius represents an extreme case of this feedback. The energy injected into intergalactic space by its jets is affecting a region 16 million light-years across. Any gas in that region is being heated and stirred by the lobes, preventing it from settling into galaxies and forming stars. This has implications for the formation and evolution of galaxies in that region of space. Alcyonius isn't just passively sitting there. It's actively shaping its cosmic neighborhood over millions of years. The lobes are like cosmic bulldozers, pushing gas around, heating it up, and preventing it from collapsing under its own gravity. This affects not just the host galaxy, but also any nearby galaxies that might be trying to pull in gas to form stars. If you're a smaller galaxy trying to grow, and you're sitting in or near one of Alcyonius's lobes, you're going to have a hard time. The gas you need is too hot and too disturbed to easily fall into your gravitational well. You'll form stars more slowly than you otherwise would. Over billions of years, this can significantly affect how galaxies in this region evolve. And this is playing out across the universe. Alcyonius is just one example, an extreme one. But the same process happens around every active black hole. Jets from smaller radio galaxies heat smaller volumes of space. Radiation from accreting black holes that don't launch jets still heats the surrounding gas. All of it adds up to a universe where black holes play a crucial role in regulating star formation and shaping the properties of galaxies. It's one of the great insights of modern astrophysics. Black holes aren't just exotic objects sitting at galactic centers doing nothing. They're active participants in galaxy evolution. They grow along with their galaxies, and they influence how those galaxies develop over time. Understanding this connection between black holes and galaxies is one of the major goals of current research. How exactly do black holes and galaxies co-evolve? What determines when a black hole starts feeding and launching jets? How does the energy from jets and radiation distribute itself through the surrounding gas? These are questions astronomers are actively working on, using observations of thousands of galaxies at different stages of evolution and sophisticated computer simulations that model the physics involved. Another thing Alcyonius tells us is that we still have a lot to learn about the universe. This galaxy was discovered in 2022, very recently. The data showing it had existed for years in archives, but nobody had recognized what they were seeing. It took new analysis techniques, new ways of processing radio data, to reveal the full extent of the structure. This raises a question. How many other giant structures are out there waiting to be found? Are there galaxies even larger than Alcyonius, hiding in existing data or waiting in future surveys? The universe is vast, and we've only surveyed a small fraction of it at the depth and sensitivity needed to find objects like this. As telescopes improve, as data processing techniques advance, as surveys cover more of the sky at higher resolution, we'll likely find more extreme examples. Alcyonius might hold the record for now, but that record could be broken. There could be an even larger radio galaxy out there, its lobes extending 20 million light-years, 30 million light-years, perhaps even farther. We won't know until we look. And looking requires resources, time, and people dedicated to searching through vast amounts of data. The Square Kilometre Array, a radio telescope network currently under construction in South Africa and Australia, will be far more sensitive than LOFAR. When it comes online in the coming years, it will be able to detect fainter and more distant radio sources. It might find giant radio galaxies that are too faint for current telescopes to see. It might find galaxies like Alcyonius in the very distant universe, as they appeared billions of years ago. And that would tell us whether giant radio galaxies were more common in the early universe or whether they're a recent phenomenon. There's also the question of how common these giant radio galaxies are. Alcyonius is exceptional because it's so large, but there are thousands of known radio galaxies, and new ones are being discovered regularly. Most are much smaller than Alcyonius, but they're all powered by the same basic mechanism: supermassive black holes launching jets. Current surveys suggest that giant radio galaxies, those larger than about 2.3 million light-years, make up about 10% of all radio galaxies. So they're not incredibly rare, but they're not common either. Alcyonius, being 16 million light-years across, is exceptional even among giants. Understanding the statistics, what fraction of radio galaxies grow to what sizes, helps astronomers understand the physics of jets, the properties of intergalactic space, and the life cycles of supermassive black holes. If giants are more common in certain environments, maybe in low-density regions or in galaxy clusters, that tells us something about how environment affects jet evolution. If giants are more common at certain periods in cosmic history, that tells us something about how galaxy and black hole evolution has changed over time. These are questions that require large surveys, observations of thousands or tens of thousands of radio galaxies, and statistical analysis to tease out the patterns. Alcyonius is a data point in that larger effort. It's the extreme example, the one that pushes the boundary, but understanding why it's extreme requires understanding the full population of radio galaxies. Now, let's think about what Alcyonius can tell us about the history of the universe. We see Alcyonius as it was 3 billion years ago. At that time, the universe was about 10.8 billion years old, roughly 78% of its current age. This was a period when the universe was still actively forming galaxies. The peak of star formation in the universe happened between about 8 and 12 billion years ago. Before that, most of the gas in the universe was too hot and diffuse to collapse and form stars efficiently. After that peak, star formation gradually declined as galaxies used up their gas and as expansion spread everything farther apart. 3 billion years ago, when the light we're seeing from Alcyonius left that galaxy, the universe was in the declining phase of this star formation history. Galaxies were still forming stars, but not at the furious rates seen earlier. Large galaxies like Alcyonius's host were mostly assembled by this point. They had undergone most of their major mergers, and their supermassive black holes had grown to substantial sizes. But there was still plenty of gas around, both within galaxies and in the intergalactic medium. This gas could feed black holes, allowing them to launch jets like we see in Alcyonius. At earlier times, even more giant radio galaxies might have existed. When the universe was younger, galaxies were closer together, and mergers were more common. Mergers dump gas into galactic centers, feeding black holes and triggering jet activity. So, it's possible that giant radio galaxies were more common in the early universe. But there's a problem with observing them. The farther back in time you look, the harder it is to detect faint, extended structures. The signal gets weaker, the structures appear smaller on the sky, and they're harder to distinguish from background noise. So, we might be missing most of the giant radio galaxies from the early universe simply because they're too faint and too distant for our current telescopes to detect. Future telescopes might change this. The James Webb Space Telescope, launched in 2021, observes in infrared wavelengths and can see extremely distant galaxies as they appeared less than 1 billion years after the Big Bang. While it doesn't observe radio wavelengths, it can identify distant galaxies that might host radio jets. Combining observations from Webb with radio observations from LOFAR or the Square Kilometre Array could reveal distant giant radio galaxies. Finding them would tell us about the conditions in the early universe, about how quickly supermassive black holes grew, and about how feedback from jets shaped early galaxy formation. There's also the question of what happened before Alcyonius became a radio galaxy. Its host galaxy is an elliptical, a type of galaxy formed through major mergers. When two spiral galaxies collide and merge, the resulting galaxy is usually elliptical. The organized rotation of the spirals gets disrupted, stars get scattered into more random orbits, and the gas gets consumed in bursts of star formation. Alcyonius's host was likely formed through at least one major merger, possibly several. Each merger would have dumped gas into the galactic center, feeding the black hole. And at some point, the black hole started launching jets, creating the enormous lobes we see today. But before that, before the jets turned on, the galaxy would have looked quite different. It would have been a relatively ordinary elliptical galaxy, possibly with an active galactic nucleus emitting radiation, but without the giant radio lobes. The transition from a normal galaxy to a radio galaxy involves changes in the black hole's feeding rate and in the magnetic fields around it. We don't fully understand what triggers this transition. Is it a merger that dumps fresh gas onto the black hole? Is it a change in the galaxy's environment that allows gas to flow inward? Is it something about the black hole's spin or the configuration of its accretion disk? These are open questions. We know that not all elliptical galaxies become radio galaxies. only about 10% of ellipticals show strong radio emission. So there's something special about the galaxies that do launch jets, but we're still working out exactly what that is. Studying large samples of radio galaxies and comparing them to non-radio ellipticals helps narrow down the possibilities. And Alcyonius, as an extreme example, gives us clues about what conditions are needed to create not just jets, but exceptionally powerful and long-lived jets. Let me also talk about the role of dark matter in all of this. Dark matter is the invisible stuff that makes up about 85% of all the matter in the universe. We can't see it directly because it doesn't emit, absorb, or reflect light. But we know it's there because of its gravitational effects. Galaxies rotate faster than they should based on their visible matter alone. Galaxy clusters contain more mass than we can account for with visible matter. Light from distant galaxies gets bent by invisible mass, gravitational lensing that reveals dark matter's presence. All of this points to the existence of dark matter surrounding and permeating galaxies. Alcyonius, like every galaxy, is embedded in a dark matter halo. This halo extends far beyond the visible galaxy, possibly several million light-years. The total mass of dark matter in Alcyonius's halo is much larger than the mass of visible matter, stars and gas, in the galaxy itself. Dark matter doesn't interact with the jets directly. Jets are made of normal matter, protons and electrons, which don't significantly interact with dark matter. But dark matter does affect the overall environment. It determines the gravitational potential, the shape of space-time around the galaxy. It influences how gas flows, both within the galaxy and in the surrounding intergalactic space. And it plays a role in galaxy mergers, which, as we've discussed, likely contribute to the formation of elliptical galaxies and the feeding of supermassive black holes. When two galaxies merge, their dark matter halos merge too. The dark matter halos collide and pass through each other because dark matter particles don't interact strongly except through gravity. But the visible matter, the gas and stars, experiences friction and collisions. This difference in behavior is important. It affects how mergers play out and how gas ends up in galactic centers. Computer simulations of galaxy mergers include both visible matter and dark matter, tracking how they behave differently and how they influence each other. These simulations show that the details of the merger, the mass ratio of the two galaxies, their orientations, their dark matter distributions, all affect the outcome. In some mergers, lots of gas ends up in the center, feeding the black hole. In others, the gas gets dispersed or consumed in star formation before it can feed the black hole. Understanding these details helps explain why some galaxies become radio galaxies and others don't. Alcyonius's dark matter halo also affects the large-scale structure around the galaxy. Dark matter forms filaments and nodes in the cosmic web, the large-scale structure of the universe. Galaxies form where dark matter is densest, in halos and along filaments. Alcyonius sits within this structure, connected to the cosmic web through its dark matter halo. And the distribution of dark matter around Alcyonius influences how intergalactic gas is distributed, which in turn affects how easily the jets can expand and inflate the lobes. If Alcyonius is in a relatively empty region, a cosmic void, the dark matter density is lower, the gas density is lower, and the jets can expand farther before being stopped. This is one of the proposed explanations for Alcyonius's extreme size. Dark matter, also affects the gravitational environment on larger scales. Alcyonius is part of a large-scale structure that includes thousands of other galaxies. Over billions of years, these galaxies are all moving through the cosmic web, following trajectories determined by the gravitational pull of dark matter. Alcyonius itself is moving through space. All galaxies are carried along by the expansion of the universe and by the gravitational attraction of nearby massive structures. This motion can affect the jets. If the galaxy is moving through the intergalactic medium, the jets can get bent in the direction opposite to the galaxy's motion, creating a curved or swept-back appearance. Alcyonius's jets appear relatively straight, suggesting the galaxy isn't moving very fast through the surrounding medium, or that the medium is very thin. Let me give you a sense of what it would be like to actually travel through Alcyonius. Not that we ever could, but as a thought experiment to really grasp the scale. Imagine you had a spacecraft capable of traveling at the speed of light. Nothing with mass can actually do this. Einstein's theory of relativity forbids it, but let's imagine it anyway. You start at one edge of Alcyonius, at the tip of one radio lobe, millions of light years from the host galaxy. Around you, there's almost nothing. Space at this distance from the host galaxy is incredibly empty. You're in intergalactic space, the vast voids between galaxies. The nearest stars are millions of light years away in other galaxies. If you looked back toward the Milky Way, it would be a faint smudge, billions of light years distant, completely invisible without powerful telescopes. The stars you'd see are from nearby galaxies, distant points of light scattered across the blackness. The nearest might be hundreds of thousands of light years away. You're surrounded by a faint glow of radio emission, invisible to your eyes but detectable with instruments. This is the edge of the lobe, the outer boundary where the jet's influence is starting to fade. The plasma here is extremely tenuous. If you held out your hand, palm up, only a few atoms per second would land on it. That's how empty this space is. But it's not completely empty. There are energized particles, electrons, and protons accelerated by the jets long ago. There are magnetic fields threading through the region, weak but measurable. And there's a faint glow of radiation across multiple wavelengths. You start moving toward the host galaxy, traveling at light speed, 186,000 miles per second. At this speed, you could circle the Earth 7.5 times in 1 second. You could reach the Moon in 1.3 seconds. You could reach the Sun in 8 minutes and 20 seconds. You're traveling faster than anything with mass has ever traveled, faster than the fastest spacecraft, faster than anything humans have built. And yet, in the context of Alcyonius, you're barely moving. Days pass. You've traveled hundreds of billions of miles. The distance from Earth to the Sun, 93 million miles, is now trivial. You've crossed that distance thousands of times. But you're still in the lobe. The glow around you is exactly the same. You're no closer to the host galaxy than when you started, at least not noticeably. Weeks pass, then months. You've now traveled trillions of miles, distances that would take conventional spacecraft thousands of years to cover. But you're still in the lobe. The host galaxy is still too far away to see. You're surrounded by the same faint radio glow, the same near emptiness. Years pass. You're still traveling at light speed, covering 6 trillion miles every year, the distance light travels in 1 year. The glow around you is gradually, imperceptibly intensifying. You're moving deeper into the lobe, where the plasma is very slightly denser and the magnetic fields are marginally stronger. But the change is so gradual that you wouldn't notice it from day to day or even from month to month. Decades pass. You've been traveling for 50 years now, covering 300 trillion miles. You could have traveled from the Sun to the nearest star, Proxima Centauri, more than 10 times over. But you're still inside the lobe, still surrounded by near emptiness. Still so far from the host galaxy that you can't see it yet. Centuries pass. 100 years, 200 years, 500 years. The glow is brighter now, at least in radio wavelengths. You're approaching the region where the jet itself is still narrow and focused, where plasma is being actively pumped outward from the black hole. But you're still millions of light years from the source. Millennia pass. 1,000 years. 10,000 years. You've now been traveling for longer than all of recorded human civilization, longer than we've had agriculture, writing, cities, or technology. The entire span of human history could have played out multiple times since you started this journey. And you're only now about halfway through the lobe. The host galaxy is finally becoming faintly visible ahead of you. It's still millions of light years away, but it's there, a tiny smudge of light in the darkness. You keep traveling. 100,000 years pass. 1,000,000 years. You've been traveling for longer than the human species has existed. Longer than our genus, Homo, has existed. If you had started this journey when our earliest upright walking ancestors first appeared, you still wouldn't be at the host galaxy yet. You're finally approaching the boundary between the lobe and the galaxy proper. The plasma around you is thinning as you leave the lobe behind. Ahead, the host galaxy is getting brighter. You can start to make out its structure. It's an elliptical galaxy, a vast collection of stars without the spiral structure of the Milky Way. 2 million years pass. You're now entering the outer regions of the galaxy itself. The stars here are spaced far apart, maybe several light years between each one. But compared to the emptiness you've been traveling through, this is crowded. You occasionally pass within a few light years of a star, close enough to see it as more than just a point of light. Each star might have planets orbiting it, worlds you're passing in the night without ever seeing. 3 million years. You're deeper into the galaxy now. The stars are more densely packed. You're passing dozens of stars every few years. If there were civilizations on planets around these stars, they might detect your passage, a strange object moving at light speed through their system. 4 million years. You're approaching the central regions of the galaxy where the density of stars is highest. Here, stars are separated by just a light year or less. The night sky, if you were standing on a planet here, would be spectacular. Thousands of bright stars, much brighter than anything we see from Earth, filling the sky. And at the very center, you finally reach the supermassive black hole. The source of all this. The engine that created the entire structure you've been traveling through for millions of years. The black hole itself is invisible, a region of space-time only a few light hours across where nothing can escape. But around it, you see the accretion disk, a swirling maelstrom of superheated gas glowing brilliantly in visible light, X-rays, and gamma rays. And launching from the poles of this disk, you see the jets. twin beams of plasma, each one narrower than the solar system, but extending in opposite directions for millions of light years. You've just traveled the full length of one of these jets. And now, you'd need to travel another 8 million years at light speed to reach the opposite edge of Alcyonius, to cross the other lobe and emerge on the far side. The entire journey, at the fastest speed physically possible for anything, would take over 16 million years. 16 million years of continuous travel at light speed just to cross from one end of this structure to the other. That's the scale we're dealing with when we talk about Alcyonius. That's how incomprehensibly vast this galaxy is. And remember, nothing with mass can actually travel at light speed. Any real spacecraft would travel much, much slower. The Voyager 1 probe, the most distant human-made object, is traveling at about 38,000 miles per hour. At that speed, crossing Alcyonius would take roughly 3 trillion years. That's about 200 times longer than the current age of the universe. The universe would have to exist 200 times longer than it already has for Voyager to make the crossing. By that time, all stars would have burned out. Galaxies would have dispersed. The universe would be a cold, dark, empty place. And Voyager still wouldn't have finished crossing Alcyonius. This is the brutal reality of cosmic distances. Even the speed of light, the ultimate speed limit, is painfully slow on these scales. Now let's talk about the future of Alcyonius, because like everything in the universe, it won't last forever. Right now, Alcyonius's jets are active, pumping energy into the lobes and keeping them bright. But supermassive black holes don't feed continuously forever. Eventually, the supply of gas falling into the black hole will diminish. Maybe the galaxy will run out of easily accessible gas in its central regions. Maybe a change in the galaxy's environment will cut off the inflow. Maybe a merger with another galaxy will temporarily disrupt the feeding process. Whatever the cause, at some point, the jets will weaken and eventually shut off. When that happens, the lobes will begin to fade. The plasma will gradually lose energy, the electrons will slow down, and the synchrotron radiation will dim. Over millions of years, the lobes will expand and cool, becoming fainter and fainter until they're no longer detectable. The vast structure that makes Alcyonius the largest galaxy we've ever found will dissolve back into the intergalactic medium. The energy will disperse, the magnetic fields will weaken, and the plasma will mix with the surrounding gas. Eventually, there will be no trace of the lobes at all, just a relatively ordinary elliptical galaxy floating in space. Future astronomers looking at that galaxy billions of years from now might never know. It once had lobes stretching 16 million light-years. Unless they find historical records, or unless they detect some subtle signature left behind in the surrounding environment, the evidence will be gone. This is the fate of all radio galaxies. They're transient structures, lasting millions of years, but not billions. On cosmic timescales, they're brief. But while they exist, they're spectacular, and they have a real impact on their surroundings. The energy Alcyonius has pumped into intergalactic space will have heated gas, prevented stars from forming, and altered the evolution of smaller galaxies in its vicinity. That influence persists even after the lobes fade. There's also the question of what happens to the host galaxy and its black hole. Alcyonius sits 3 billion light-years away, which means it's part of the large-scale structure of the universe. It's embedded in a web of galaxies, galaxy clusters, and filaments that make up the cosmic web. Over time, the host galaxy might merge with other galaxies. Galaxy mergers are common over billions of years. When galaxies merge, their black holes eventually sink to the center of the merged galaxy and spiral toward each other. If they get close enough, they merge, releasing gravitational waves and creating an even larger black hole. Alcyonius's black hole could undergo this process multiple times over the next several billion years, growing larger with each merger. And each time, after the merger settles down, the new combined black hole might start feeding again, launching new jets and creating new radiolobes. So Alcyonius's current lobes will fade, but the galaxy and its black hole will continue to exist and evolve. The story doesn't end when the jets shut off. It's just one chapter in a much longer history. Let's zoom out even further and think about what Alcyonius tells us about the universe as a whole. Alcyonius is an example of large-scale structure, but it's not the largest structure in the universe. That title belongs to things like the Hercules Corona Borealis Great Wall, a massive structure of galaxies spanning roughly 10 billion light-years, or the Sloan Great Wall, another enormous structure of galaxies stretching about 1.4 billion light-years. These are collections of thousands of galaxies arranged in sheet-like or filamentary structures. They're not single objects the way Alcyonius is. They're not coherent structures created by one physical process. They're statistical patterns in the distribution of galaxies, overdensities in the cosmic web. But Alcyonius is the largest single galaxy, the largest coherent structure associated with one central object, one supermassive black hole. And it shows us that the universe operates on scales that are genuinely difficult for human minds to grasp. We live on a planet that's about 8,000 miles across. That's tiny on cosmic scales, but it's our entire world. Every continent, every ocean, every mountain range, every city, every person we've ever known, all of it fits within those 8,000 miles. Our solar system, if you include the Oort cloud of comets surrounding it, extends about 1 light-year from the Sun. That's enormous compared to Earth. It's about 5.9 trillion miles from end to end. If Earth were a grain of sand, the solar system would be several miles across. Our galaxy, the Milky Way, is 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars, each one potentially surrounded by planets. The Milky Way is so large that light takes 100,000 years to cross from one side to the other. Human civilization has existed for maybe 10,000 years. In the time humans have built cities, developed writing, created technology, and explored our planet, light from one side of the Milky Way has traveled 1/10 of the way across. And Alcyonius is 163 times larger than that. 163 Milky Ways, end to end, would equal the span of Alcyonius. If you made a scale model where the Milky Way was the size of a dinner plate, Alcyonius would stretch the length of more than 4 football fields. If the Milky Way were a mile across, Alcyonius would be 163 miles long, the distance from one major city to another. These comparisons help, but they still don't fully capture the scale, because Alcyonius isn't a solid object. It's not like a dinner plate or a football field. It's mostly empty space, threaded with faint plasma and magnetic fields. The density is so low that if you were floating in the middle of one of the lobes, you'd have no way of knowing you were inside anything at all. You'd see distant galaxies in every direction, points of light billions of light years away. You wouldn't see the lobe itself because it's invisible at optical wavelengths. Only with a radio telescope could you detect the faint glow surrounding you. And yet, this structure exists. It's real. It was created by physical processes, jets of plasma launched from a supermassive black hole and expanding through intergalactic space for tens of millions of years. The fact that we can detect it from 3 billion light-years away is remarkable. The fact that we can measure its size, understand what created it, and use it to learn about black holes, jets, and the intergalactic medium is even more remarkable. This is what science does. It lets us reach across vast distances, across billions of years of time, and understand things that seem completely beyond human scale. We're tiny creatures on a tiny planet, and yet we've built telescopes that can see Alcyonius. We've developed theories that can explain what we're seeing, equations that describe the physics of jets, the behavior of plasma, the expansion of lobes through intergalactic space. We've created technologies that let us process terabytes of data, sift through millions of radio sources, and find the signal of Alcyonius hidden in the noise. And through all of that, we've discovered something extraordinary, a galaxy so large it challenges our imagination. There's something profound about that. The universe doesn't care whether we understand it or not. It doesn't exist for our benefit. Alcyonius would be out there, whether we discovered it or not, whether we built radio telescopes or not, whether we developed the mathematics to describe it or not. But we did discover it. We looked, we analyzed, and we found something extraordinary. And now we can share that discovery, talk about it, marvel at it, and use it to deepen our understanding of how the universe works. That's what science is at its core. It's not just about collecting facts or making measurements, though those are important. It's about satisfying that deep human need to understand, to make sense of the world and the cosmos we find ourselves in. Humans have been looking up at the sky and wondering about it for as long as we've existed. Ancient civilizations created myths and stories to explain the stars, the planets, the movements of celestial objects. They didn't have the tools or knowledge to understand what they were seeing, but they had the curiosity, the desire to make sense of it. That same curiosity drives modern astronomy. We have better tools now, telescopes that can see across billions of light years, instruments that can detect wavelengths invisible to our eyes, computers that can process vast amounts of data. But the fundamental drive is the same. We want to understand. We want to know what's out there, how it works, how it came to be. Alcyonius is a piece of that puzzle. It's one data point among many, but it's an important one. It shows us the extremes of what's possible, the upper limits of galaxy size, the immense power of supermassive black holes, and the subtle interplay between galaxies and their environments. Every discovery like this pushes the boundaries of our knowledge a little further. We learn something new, we ask new questions, and we design new observations to try to answer those questions. What determines the maximum size a radio galaxy can reach? Is there a limit? Or could galaxies even larger than Alcyonius exist? How do the jets maintain their coherence over such enormous distances? Why are giant radio galaxies more common in some environments than others? What happens to the energy pumped into the lobes after the jets shut off? These are questions astronomers are working on now, questions inspired by discoveries like Alcyonius. And the process continues, generation after generation. building on what came before. Someday, maybe decades from now, maybe centuries, astronomers will look back at the discovery of Alcyonius as a milestone, a moment when we realized just how large these structures could become, when we pushed our understanding of radio galaxies to a new extreme. They'll have better telescopes by then, telescopes we can't even imagine today. They'll have better theories, more complete models of how black holes, jets, and galaxies interact. They'll have a more complete picture of the universe, its history, its structure, its fate. But they'll remember Alcyonius as the first time we found a galaxy this enormous. The first time we saw something that stretched 16 million light-years across space. And maybe, just maybe, they'll find something even larger. The universe is vast, far vaster than Alcyonius, and there's always the possibility that something even more extreme is out there waiting to be discovered, waiting in data that hasn't been fully analyzed yet, waiting in surveys that haven't been conducted yet, waiting for telescopes that haven't been built yet. The history of astronomy is full of records being broken, of discoveries that seemed extreme until something even more extreme was found. The largest known star keeps getting bigger as we find larger and larger ones. The most distant galaxy keeps getting more distant as we look farther back in time. The most massive black hole keeps getting more massive as we find new supermassive behemoths. For now, though, Alcyonius holds the record for the largest galaxy. And it's a record that fills me with awe every time I think about it. 16.3 million light-years from one end to the other. 163 Milky Ways, laid end to end. A structure so large that light, the fastest thing in the universe, takes over 16 million years to cross it. 16 million years. Let me put that in a different context. 16 million years ago, Earth was in the middle of the Miocene epoch. The climate was warmer than today. Grasslands were spreading across continents. The ancestors of modern horses, dogs, bears, and many other mammals were evolving. Our own ancestors were small apes living in forests in Africa. There were no humans, not even close. The entire story of human evolution, from those small apes to modern civilization, has happened in less time than it takes light to cross Alcyonius. The entire story of our species, Homo sapiens, from our origins in Africa about 300,000 years ago to today, is a tiny fraction of that time. Written history, the past 5,000 years of human civilization, is an even smaller fraction. Your entire life, everyone you've ever known, every event you've experienced, all of it happens in what is, on the time scale of Alcyonius, an immeasurably brief instant. And yet, here you are, learning about Alcyonius, understanding, at least intellectually, what it is and how large it is. That's extraordinary. That's what makes us human. The ability to comprehend things far beyond our immediate experience, to understand scales of space and time that dwarf our existence. We can't directly experience what it's like to cross 16 million light-years. We can't directly perceive radio waves or magnetic fields or jets of plasma traveling at 99% of light speed. But we can understand them. We can measure them, model them, and explain them. And through that understanding, we can appreciate the universe in ways that would have been impossible for our ancestors. They looked up at the same sky we do, saw the same stars, wondered about the same cosmos. But they didn't have the tools to understand what they were seeing. We do. And that understanding is a gift, a product of thousands of years of human curiosity, ingenuity, and hard work. Every telescope ever built, every theory ever developed, every observation ever made. It all contributes to our current understanding. And Alcyonius is part of that understanding. It's a testament to how far we've come and a reminder of how much more there is to learn. Let me leave you with one final thought. When you look up at the night sky, you're seeing stars in our galaxy. Most of those stars are within a few thousand light years of Earth. The most distant stars you can see with your naked eye are maybe 15 or 20,000 light years away. That's a tiny fraction of the Milky Way's 100,000 light-year diameter. And it's an infinitesimal fraction of Alcyonius. If you could somehow see Alcyonius with your naked eye, if it were close enough and bright enough and visible at optical wavelengths, it would span a significant portion of the sky. It would be larger than any constellation you're familiar with. Larger than Orion or Ursa Major or the Southern Cross. Larger than the band of the Milky Way that stretches across our night sky. It would dominate the view, an enormous structure testifying to the power of a black hole 400 million times more massive than our Sun. But we can't see it with our eyes, of course. It's 3 billion light years away, farther than we could ever hope to travel. And it's invisible at optical wavelengths, emitting its light in radio frequencies our eyes can't detect. But we can see it with radio telescopes. We can measure it, study it, and understand it. And through that understanding, we can appreciate just how extraordinary the universe is. Before I wrap up, I want to talk about some of the other giant radio galaxies that have been discovered, because Alcyonius isn't alone. It's the largest, but there are others that come close, and each one teaches us something different about how these structures form and evolve. The previous record holder was a galaxy called Alcyonius. Actually, let me correct that. The previous record holder before Alcyonius was discovered in 2022 was a galaxy designated 3C236. This galaxy has lobes extending about 15 million light-years, just slightly smaller than Alcyonius. It was discovered using the giant Metrawave radio telescope in India, another interferometric radio telescope array. 3C236 is also about 3 billion light-years away, similar to Alcyonius. Its host galaxy is also an elliptical, and its black hole has a similar mass. The fact that it's almost as large as Alcyonius, but was discovered first, shows how much luck is involved in these discoveries. Depending on exactly how you process the data, on what sensitivity you achieve, on what region of sky you're observing, you might find one giant and miss another. There's also a galaxy called 3C236. No, wait. I already mentioned that one. Let me talk about another giant, J1420-0545. This is a mouthful, which is why astronomers often just refer to these galaxies by their catalogue numbers. J1420-0545 is about 12 million light-years across, smaller than Alcyonius, but still enormous. What makes it interesting is that it's much farther away, about 7 billion light-years. At that distance, we're seeing it as it was 7 billion years ago, when the universe was roughly half its current age. The fact that giant radio galaxies existed even back then tells us that the processes creating them, black hole feeding, jet launching, lobe inflation, were already well established in the early universe. Another fascinating giant is NGC 621, a galaxy only about 250 million light-years away. That's practically in our cosmic backyard compared to Alcyonius. NGC 621 has lobes extending about 1.2 million light-years, much smaller than Alcyonius, but still larger than most galaxies. Because it's so much closer, we can study it in much more detail. We can see the structure of the lobes more clearly, measure the properties of the plasma more accurately, and track changes over time. Observations of NGC 621 have revealed that the lobes have internal structure. They're not uniform. They have bright spots and filaments, regions where the plasma is denser or the magnetic fields are stronger. There are also shock fronts visible at the leading edges of the lobes, places where the expanding plasma is colliding with the intergalactic medium. These detailed observations help us understand the physics of lobe expansion and energy dissipation. And they give us clues about what might be happening in more distant giants like Alcyonius, where we can't see the structure as clearly. There are also radio galaxies that, while not as large as Alcyonius in terms of lobe extent, have other extreme properties. Cygnus A, for example, is one of the brightest radio sources in the sky. It's about 600 million light-years away, and its lobes extend about 300,000 light-years from the host galaxy. That's relatively small for a giant radio galaxy, but the jets in Cygnus A are incredibly powerful. They're pumping out more energy than almost any other known radio galaxy. The lobes of Cygnus A are also much denser than those of Alcyonius. They contain more plasma, more energy, and produce much brighter radio emission. If Alcyonius is like a vast, diffuse cloud, Cygnus A is like a compact, intense fireball. Both are powered by supermassive black holes, but the details of how they feed and how the jets interact with their environment create very different outcomes. Studying the full range of radio galaxies, from small to giant, from faint to bright, from nearby to distant, helps astronomers understand the physics governing these systems. It's not enough to just find the largest one and call it a day. We need to understand the full population, the statistical distribution of sizes, powers, and properties. That's how science works. One data point, even an extreme one like Alcyonius, doesn't tell the whole story. You need many data points, many examples, to see the patterns and understand the underlying physics. Alcyonius is valuable precisely because it's an outlier. It shows us the extreme end of what's possible. But to understand why it's an outlier, we need to compare it to more typical radio galaxies. We need to ask, what's different about Alcyonius? What conditions allowed it to grow so large when most radio galaxies remain smaller? Is it the black hole mass? Probably not, since Alcyonius's black hole isn't particularly massive compared to others. Is it the jet power? Possibly, but we'd need to measure the power more precisely to be sure. Is it the environment? This seems likely, since Alcyonius appears to be in a relatively empty region of space. Is it simply time, the jets having stayed active longer than average? Also possible, though hard to prove without knowing the exact age of the jets. These questions drive ongoing research. Astronomers are surveying the sky to find more giants, building larger samples to analyze statistically. They're using computer simulations to model how jets expand through different environments, testing whether the environmental hypothesis can explain Alcyonius's size. They're measuring the properties of intergalactic gas around radio galaxies to see if there's a correlation between gas density and lobe size. And they're looking for giants at different cosmic epochs, different distances, to see whether giant radio galaxies were more or less common in the past. All of this work takes time, resources, and collaboration between many astronomers. It requires access to powerful telescopes, advanced data processing capabilities, and theoretical expertise. But it's how we make progress, how we move from discovery to understanding. Alcyoneus was discovered in 2022. That's very recent. The analysis is still ongoing. Papers are being written, data is being shared, and other astronomers are using the discovery to inform their own research. In a few years, we'll know much more about Alcyoneus than we do now. We'll have better measurements of its properties, more detailed models of how it formed, and a clearer understanding of what makes it exceptional. And maybe, in the process, we'll discover something even larger. Now, let me address something that might be on your mind. Why does any of this matter? Why should you care about a galaxy 3 billion light-years away? A galaxy so distant that the light we're seeing from it is older than the Earth? It's a fair question. Alcyoneus has no direct impact on your daily life. It's not going to affect the weather, the economy, or your personal relationships. You can't visit it, can't interact with it in any way. So why spend time learning about it? The answer, I think, is that understanding the universe is inherently valuable. Humans are curious by nature. We want to know how things work, where we came from, what our place is in the cosmos. These aren't practical questions in the sense of helping us build better technology or grow more food, but they're fundamental questions about our existence, and answering them enriches our lives in ways that are hard to quantify. When you learn about Alcyoneus, when you grasp, even imperfectly, the scale of this galaxy and the processes that created it, you're expanding your understanding of reality. You're seeing beyond the narrow confines of your immediate experience. You're connecting with something vast and ancient and utterly indifferent to human concerns. And there's a kind of beauty in that. There's also practical value, though it's indirect. The technologies developed for radio astronomy have applications beyond astronomy. Radio interferometry, the technique used to discover Alcyoneus, has been adapted for medical imaging, communications, and remote sensing. The data processing methods used to sift through terabytes of radio observations have been applied to other fields dealing with big data, from genomics to climate science. The mathematics and physics developed to understand jets and plasmas have found uses in fusion energy research and space weather prediction. So, even though Alcyoneus itself is purely a scientific curiosity, the process of discovering and studying it drives innovation in ways that do have practical impact. But more than that, understanding Alcyoneus and galaxies like it helps us understand our own cosmic context. The Milky Way, our home galaxy, is a relatively normal spiral galaxy. It doesn't have prominent radio lobes like Alcyoneus. Its central black hole, Sagittarius A, is much less active. But billions of years ago, the Milky Way might have been different. It might have had an active galactic nucleus, jets, and lobes. Evidence suggests that Sagittarius A was more active in the past, feeding more rapidly and producing more energetic outflows. Those outflows shaped the Milky Way's evolution, regulating star formation and distributing heavy elements through the galaxy. And in the future, the Milky Way's black hole might become active again. If a large amount of gas falls into the galactic center, perhaps triggered by a merger with another galaxy, Sagittarius A could start feeding again. It could launch jets like those in Alcyoneus, though probably not as large. Understanding radio galaxies helps us understand this part of galactic evolution, the phases when central black holes are active and the lasting effects they have on their host galaxies. There's also the broader context of cosmic evolution. The universe has changed dramatically over its 13.8 billion year history. In the early universe, galaxies were smaller, black holes were growing, and the first stars were forming. The intergalactic medium was denser, and galaxy mergers were more common. Over time, galaxies grew larger through mergers. Black holes grew more massive, star formation peaked and then declined, and the universe expanded, spreading everything farther apart. Radio galaxies like Alcyonius are snapshots of this evolution. Each one we observe is frozen at a particular moment in cosmic history. By studying radio galaxies at different distances, at different look-back times, we can trace how they've changed over billions of years. We can see whether giant radio galaxies were more or less common in the past, whether jets were more or less powerful, whether feedback was more or less effective at regulating star formation. This is cosmology, the study of the universe as a whole, its structure, its history, and its fate. And every galaxy we study, every object we observe, contributes to that understanding. Alcyonius is one piece of the puzzle, an important piece because it's so extreme, but still just one piece. Now let me talk about something equally important: how we actually know Alcyonius is as large as we claim. This is crucial because science isn't about taking things on faith. It's about evidence, observation, and verification. So how do we measure something 16 million light-years across when it's 3 billion light-years away? The answer involves a combination of techniques, each building on the others. First, we need to determine the distance to Alcyonius. At 3 billion light-years, the galaxy is far too distant for direct parallax measurements, the technique used for nearby stars. Instead, we use redshift, the stretching of light caused by the expansion of the universe. When we observe Alcyonius's host galaxy, we can see spectral lines, characteristic patterns of light emitted by hydrogen, oxygen, and other elements in the galaxy's stars and gas. These lines appear at longer wavelengths than they would if the galaxy were at rest relative to us. The amount of shift tells us how much the universe has expanded since the light left the galaxy. And using cosmological models that relate expansion to distance, we can calculate how far away the galaxy is. For Alcyonius, the redshift is approximately 0.25. That corresponds to a light travel distance of about 3 billion light-years. More precisely, it's about 2.85 billion light-years, but 3 billion is close enough for most purposes. Once we know the distance, we can convert angular size to physical size. When we observe the radio lobes with LOFAR, we measure their angular extent on the sky. They span about 8 arc-minutes from end to end. An arc-minute is 1/60th of a degree, so 8 arc-minutes is roughly 2/10ths of a degree. For comparison, the full moon appears about half a degree across, or 30 arc-minutes. So, Alcyonius's lobes, despite being 16 million light-years across, appear smaller than the moon on the sky because they're so incredibly far away. To convert this angular size to a physical size, we use basic trigonometry. The formula is physical size equals distance times angular size, where angular size is measured in radians. 8 arc-minutes converts to about 0.0023 radians. Multiply that by the distance, roughly 3 billion light-years, and you get approximately 16 million light-years. That's the basic calculation, though the details are more complex when you account for cosmological effects. The universe is expanding, and this affects how we define distance. There are different distance measures in cosmology: light travel distance, proper distance, comoving distance, and angular diameter distance. Each one answers a slightly different question about separation in an expanding universe. For calculating the physical size of an object like Alcyonius's lobes, we use angular diameter distance. For a redshift of 0.25, accounting for the universe's expansion rate and dark energy, this comes out to about 2.3 billion light-years. Using this distance, with the observed angular size, gives a physical size of approximately 16.3 million light-years. These calculations require detailed cosmology, but the principles are well understood and tested. Now let's talk about uncertainty. No measurement in science is perfectly precise. There's always some range of possible values, some margin of error. For Alcyonius, the main source of uncertainty is defining exactly where the lobes end. The radio emission from the lobes fades gradually with distance from the jets. There's no sharp boundary, no clear edge. So where you draw the line depends on your sensitivity threshold, on how faint an emission you can reliably detect. Different analyses using different detection thresholds give slightly different sizes. Some measurements put Alcyonius at 15.8 million light-years. Others say 16.5 million light-years. The commonly cited value is 16.3 million light-years, with an uncertainty of perhaps 3 to 500,000 light-years. That sounds like a huge uncertainty, and in absolute terms it is. But it's only a few percent of the total size. It doesn't change the fundamental conclusion that Alcyonius is enormous, far larger than any other known galaxy. There's also uncertainty in the distance measurement. The redshift itself can be measured very precisely, to many decimal places. But converting that redshift to a distance requires assumptions about cosmology, about the expansion rate of the universe, about dark energy, about the overall geometry of space-time. If our cosmological model is slightly wrong, the distance would be different too. Current uncertainties in cosmological parameters translate to maybe 5 or 10% uncertainty in distance for objects at this redshift. That would propagate to a similar uncertainty in the calculated size of the lobes. But again, even with the most conservative estimates, even accounting for all these uncertainties, Alcyonius is still larger than any other galaxy we've measured. It's not a marginal case where the error bars overlap with other giants. It's decisively the largest, bigger than the previous record holder by more than 1 million light-years. This is how science works, through careful measurement, rigorous uncertainty, analysis, and independent verification. After Alcyonius was announced in 2022, other astronomers looked at the same data. They checked the measurements, verified the distance calculation, and confirmed that the lobes really do extend as far as claimed. Some teams used different radio telescopes to observe the same region, getting independent measurements that agree with the original discovery. This process of verification is crucial. One team's claim, no matter how careful they are, isn't enough. The scientific community needs to reproduce the result, check it from multiple angles, make sure it's not an error or an artifact of the analysis. And for Alcyonius, that verification has happened. The discovery stands. There's another aspect of this worth mentioning: the role of technology in enabling discoveries like this. Alcyonius couldn't have been discovered 50 years ago. We didn't have radio telescopes with the necessary sensitivity and resolution. We didn't have the computing power to process the massive datasets required. We didn't have the algorithms and techniques to extract faint extended emission from noisy data. All of these things had to be developed over decades of work by thousands of engineers, astronomers, and computer scientists. LOFAR itself represents a huge investment in radio astronomy infrastructure. Building a network of antenna stations across Europe, developing the correlation systems to combine their signals, creating the data processing pipelines, all of this took years of effort and significant funding. And the payoff is discoveries like Alcyonius. This is typical of modern astronomy. The low-hanging fruit, the easy discoveries that could be made with simple telescopes, were picked long ago. What remains requires increasingly sophisticated instruments, larger collaborations, and more advanced analysis techniques. But the rewards are worth it. Every new generation of telescopes reveals things we couldn't see before, answers questions we couldn't address, and raises new mysteries we didn't know existed. The square-kilometer array, currently under construction, will be orders of magnitude more sensitive than LOFAR. It will detect fainter radio sources, see more distant galaxies, and reveal structures that are currently invisible to us. It might find galaxies even larger than Alcyonius, or it might confirm that Alcyonius really is at the extreme upper end of what's possible. Either way, we'll learn something new. The James Webb Space Telescope, launched in 2021, is already revolutionizing our understanding of distant galaxies. It can see farther and with more detail than any previous infrared telescope. While it doesn't observe radio wavelengths, it can identify distant galaxies that might host radio jets, and combining Webb observations with radio data from LOFAR or other telescopes could reveal distant, giant radio galaxies from the early universe. There are also plans for next-generation radio telescopes, even more powerful than the square-kilometer array. Concepts for enormous space-based radio interferometers that could achieve resolutions impossible from the ground. Ideas for lunar radio arrays, telescopes placed on the far side of the moon, where they'd be shielded from Earth's radio noise. These are decades away from reality, but they show the trajectory of the field, always pushing toward better, more sensitive instruments that can reveal more of the universe. And as these instruments come online, our understanding of objects like Alcyonius will deepen. We'll measure the properties of the plasma in the lobes more precisely. We'll track changes over time, watching the lobes expand and evolve. We'll find more giants, building statistical samples that let us understand not just individual objects, but the population as a whole. We'll test our theories of jet physics, black hole feeding, and galaxy evolution against ever more detailed observations. This is the endless cycle of science. Observation leads to questions. Questions drive new observations. New observations refine our theories, and refined theories predict new phenomena to observe. Alcyonius is part of that cycle. It's a data point that tests our understanding, a discovery that raises new questions, and a stepping stone toward deeper knowledge. Before I close, I want to talk about one more thing that makes Alcyonius remarkable: the sheer improbability of its existence. Think about what had to happen for this structure to exist. First, you need a large elliptical galaxy to form, probably through the merger of multiple smaller galaxies over billions of years. Then you need a supermassive black hole at its center, grown to hundreds of millions of solar masses through accretion and mergers. Then you need gas to fall into the black hole at just the right rate, not so fast that it forms a thick disk that chokes off the jets, but fast enough to power energetic outflows. Then you need the magnetic fields around the black hole to be organized in just the right way to launch collimated jets rather than diffuse winds. Then you need those jets to remain stable and pointed in the same direction for tens or hundreds of millions of years. Then you need the galaxy to be in a relatively empty region of space, where the intergalactic medium is thin enough that the jets can expand to enormous distances. And then you need all of this to happen in a location, and at a time such that we can observe it, 3 billion years later, from a small planet orbiting a star in a different galaxy billions of light years away. Any one of these factors being different would mean Alcyonius either wouldn't exist or wouldn't be as large as it is, or wouldn't be observable by us. The fact that all these conditions were met, that this structure exists and that we found it, is remarkable. It's a reminder of how vast and varied the universe is. There are trillions of galaxies out there, and each one has its own history, its own properties, its own unique combination of circumstances. Most galaxies are unremarkable, ordinary spirals or ellipticals going about their business of forming stars and evolving slowly over billions of years. But some, like Alcyonius, are exceptional. They're the outliers, the extremes, the galaxies that push the boundaries of what's possible. And finding these extremes teaches us things we couldn't learn from studying typical galaxies. When you study only average cases, you understand the average behavior, but you don't learn about the full range of possibilities, about the extreme conditions where different physics dominates, about the edge cases that test your theories. Alcyonius is valuable precisely because it's extreme. It shows us what happens when jets stay active for an exceptionally long time, when the environment is exceptionally empty, when a galaxy reaches the upper limit of size. And studying it helps us understand the physics that operates in those extreme conditions. There's a broader lesson here about science and discovery. Progress often comes from studying outliers, from finding the strange cases that don't fit our expectations. When Henrietta Swan-Leavitt studied variable stars in the early 20th century, she noticed a pattern in a particular type of pulsating star that led to one of the most important distance measurement techniques in astronomy. When Vera Rubin studied the rotation of galaxies in the 1970s, she found that stars were moving faster than expected, leading to the discovery of dark matter. When astronomers observed distant supernovae in the late 1990s, they found the universe's expansion was accelerating, leading to the discovery of dark energy. In each case, the key was noticing something unusual, something that didn't match expectations, and investigating it thoroughly. Alcyonius might not lead to a revolution as profound as those examples, but it's part of the same process. It's an unusual object that demands explanation, and working to explain it deepens our understanding of radio galaxies, black hole jets, and the intergalactic environment. Who knows what we'll discover as we study it more? Maybe there's some new physics operating in those enormous lobes, some process we haven't accounted for. Maybe the fact that Alcyonius is so large will lead us to revise our models of jet propagation or intergalactic gas distribution. Or maybe it'll turn out that everything about Alcyonius can be explained with existing physics, that it's simply an extreme case of processes we already understand. That would be valuable too, confirming that our theories work even in these extreme conditions. Either way, we learn something. And that's the point of doing science: to learn, to understand, to expand the boundaries of human knowledge. Alcyonius is a piece of that larger effort. It's one discovery among many, one galaxy among trillions, one data point in the vast enterprise of understanding the cosmos. But it's an important piece, a remarkable galaxy, and a significant data point. And the fact that you now know about it, that you've spent this time learning about a galaxy 3 billion light-years away, that you understand, at least conceptually, what it is and why it matters, that's part of the human story too. We're the species that looks up at the sky and wonders. We're the species that builds telescopes to see farther, that develops mathematics to understand what we see, that shares knowledge across generations, so each new generation can build on what came before. We're the species that found Alcyonius, measured it, understood it, and marveled at it. And that's something to be proud of. Let me leave you with one final thought. Alcyonius is out there right now. Its jets are firing, its lobes are glowing, and its black hole is feeding. And even though it's 3 billion light-years away, even though the light we see from it is 3 billion years old, it's still there, still enormous, still growing, still pushing the boundaries of what we thought was possible. That's the universe we live in, a universe where galaxies can span 16 million light-years, a universe where black holes can launch jets that travel for hundreds of millions of years. A universe so vast and so strange that even our wildest imaginations struggle to keep up, and we get to live in it, observe it, and try to understand it. That's a privilege. That's what makes us human. The ability to look up at the sky, see something we don't understand, and then spend years, decades, centuries working to figure it out. Alcyonius is the result of that work. It's the product of countless hours of observation, analysis, and thought. And it's a reminder that no matter how much we learn, there's always more to discover. The universe is full of wonders, and Alcyonius is one of them. The biggest galaxy we've ever discovered. Bigger than your imagination, bigger than mine, but real, measurable, and out there in the cosmos, silently testifying to the incredible forces shaping our universe. Thank you for joining me on this journey across 16 million light-years of space. If this changed how you think about the scale of the universe, if it sparked your curiosity or filled you with wonder, then the time was well spent. Keep looking up at those stars. Keep asking questions. And remember, somewhere out there, 3 billion light-years away, Alcyonius is still shining, still growing, still being the largest galaxy we've ever found. And that's something worth celebrating.